Welcome viewers. Today we'll see the Coulombs law. The Coulomb states that the electric charges produce the mechanical force on each other. If the two charges are placed at a distance, then force will be developed on each other. The expression for this force and characteristics was given by the Coulombs law. First we'll see the characteristics. The like charges repel each other, but unlike charges attract each other. First point. Second one, the force is proportional to the product of the magnitude of the charges. If the two charges are available, mean the force will be proportional to Q1 and Q2. The third point, the force is inversely proportional to square of the distance between the two charges. 1 divided by r square, right? Inversely proportional to square of the distance between the charges. The force depends upon the medium in which the charges are located. Where the charge is located depends upon the medium it will act. And the last one is the force is always act along the straight line joining the 2 point charges. It will always act along the straight line. So these 5 points are given by the Coulombs, these 5 characteristics. Based on that we can go for the derivation. We'll see the diagram. So there are two charges available, Q1 and Q2. Q1 is placed at point 1, Q2 is placed at point 2. This R12 is the distance vector between Q1 and Q2. A12 is the unit vector. This F1 is the force developed on the charge 1 due to second charge. Similarly, the F2 is the force developed on Q2 due to the first charge. See the direction, both are equal but in opposite direction, right? So the expression for this force will be given by the Coulombs. Before that we'll see the unit vector. Unit vector is nothing but vector by scalar. The general formula is vector by scalar. It can be expressed in two ways, in terms of force or in terms of distance vector. In terms of force mean this F2 vector by F2. Vector by scalar. This is magnitude of F2. In terms of the distance vector, A12 vector equal to R12 vector. Now this charge Q1 and Q2 are separated by the distance R12. What we need? Two charges Q1 and Q2. The distance between the charges R12. So based on the diagram and based on the characteristics given by the Coulombs, it is that the force is directly proportional to product of magnitude of the charges Q1 and Q2. Similarly, inversely proportional to square of the distance between the charges. So F2 is directly proportional to Q1 Q2 divided by R12 square. This is based on the X point given by the Coulombs. So while equating, we need to introduce one constant, 1 divided by 4 pi epsilon. Q1 Q2 divided by R12 square. What is this epsilon? Epsilon is the permittivity. What is permittivity? The electrical energy storage is given by the permittivity. The factor given by permittivity is nothing but electrical storage of the any medium. That is epsilon naught and epsilon r. What is epsilon naught? Absolute permittivity. That will be constant, 8.854 into 10 to the power minus 12. Epsilon r is relative permittivity. That is depends upon the medium, right? So epsilon equal to epsilon naught, epsilon r. Epsilon naught means absolute permittivity, that will be 8.854 into 10 to the power minus 12. Epsilon r is relative permittivity, that is depends upon the medium, right? Now this F2 is nothing but is a scalar form. We will take this as equation 1 in a scalar form. In order to get the vector form, we can refer the unit vector. A12 unit vector equal to F2 vector by F2. Right. So cross multiply this so that A12 unit vector into F2 equal to F2 vector. Right. So this F2 vector can be written as A12 vector into F2. Now we can get the scalar vector form, F12 equal to A12 into F2. What is this? F2 is already available in equation 1. So from equation 1 we can substitute the value F2 equal to, this is nothing but now vector. Previously what we calculated is scalar. 1 divided by 4 pi epsilon q1 q2 divided by r12 square into a12 vector, a12 unit vector. Now it is in a vector form, but a12 in another form is r12 vector by r12 in terms of distance vector. So we can replace this a12 by r12 vector by r12. So finally what we got, f2 vector equal to q1 q2 divided by 4 pi epsilon r12 cube into r12 vector. This equation number 2 is completely the vector form. Equation 1 is the scalar form. The value of epsilon, permittivity, epsilon naught into epsilon r. Epsilon naught is absolute permittivity, 8.854 into 10 to the power minus 12. This relative permittivity based on the medium will take this a free space. For free space it will be 1, right? So this 8.854 into 10 to the power minus 12 into 1. For simplification I can write it as 1 divided by 36 pi into 10 to the power 9. Both are same only. For a simplification it is given in terms of pi. 1 divided by 36 pi into 10 to the power 9. Now we'll substitute this epsilon value in the second equation, vector form. So q1 q2 divided by 4 pi epsilon r12 cube into r12 is nothing but the scale vector form, equation number 2. In this we are going to substitute this epsilon value. So q1 q2 divided by 4 pi into 1 divided by 36 pi into 10 to the power 9. This value, this epsilon value is substituted, and r12 cube into r12 vector. So this can got cancelled, 4 pi and this 36 pi. So it got 9 times. So 9 into 10 to the power 9 available in the denominator. So it will go to the numerator. So 9 into 10 to the power 9. What is, by cancelling these two, here 9 will be there. 9 into 10 to the power 9 will go to numerator. So 9 into 10 to the power 9 q1 q2 divided by r12 cube into r12 vector, right? So this is nothing but force developed on the second charge f2 in a vector form. 9 into 10 to the power 9 q1 q2 divided by r12 cube into r12 vector. That equation 1 is the scalar form, q1 q2 divided by 4 pi epsilon r12 square, that is a scalar form. So while using the problem or while solving the problem based on the vector quantity or scalar quantity, whether we can use equation 1 or this equation. This is a scalar form or vector form. This is a vector form that can be used while solving the problem. Based on the data available, either we can go for vector form or scalar form, right? Then what about the f1, first force f1? We calculate, we got the expression for f2. What about f1? Both are equal and opposite. So f1 vector equal to minus f2 vector, right? Because of both are equal and opposite, the f1 can be expressed as minus of f2, 50 microcoulomb, and q2 10 microcoulomb, located at the point minus 1, 1, minus 3 and 3, 1, 0. Find the force on q1, right? Two charges available, 50 microcoulomb and 10 microcoulomb at two different points. We need to find what is the force on the q1. The diagram is available here, right? So this is q1 at located at first point minus 1, 1, minus 3. q2 available at second point 3, 1, 0. It can be written as x1 y1 z1. Similarly x2 y2 z2. So this r12 is the distance between the distance vector. What is the formula for this? 9 into 10 to the power 9 q1 q2 divided by r12 cube into r12 vector. We can use the vector form because the 2 points are available. Easily we can calculate the distance vector, so that we can use the vector form, right? So 9 into 10 to the power 9, q1 q2 values are already available. q1 is 50 microcoulomb, that is 50 into 10 to the power minus 6 coulomb. q2 is 10 microcoulomb, that is 10 into 10 to the power minus 6 coulomb. What we need is r12 vector and r12 the magnitude. We need this r12 vector, right? So other terms are already available. How will you find this r12 vector? Distance vector. R12 vector is nothing but distance vector. distance between the 2 points, very easy. Here we have x1 y1 z1, x2 y2 z2. So r12 vector can be calculated as x1 minus x2, distance vector, difference between the distance, x1 minus x2 into I vector plus y1 minus y2 into j vector plus z1 minus z2 into k vector. Right, now we can substitute the value. X1 is minus 1, x2 is minus 3, y1 is 1, y2 also 1, z1 is minus 3 and z2 is 0. So minus 1 minus 3, it becomes minus 4i. 1 minus 1 0, so 0j minus 3k. Right, so finally what we have, minus 4i vector minus 3k vector. Now we got the expression for r12 vector, minus 4i vector minus 3k vector. So this is the distance vector. How will you find the magnitude? Square root of this coefficients, right? Square root of minus 4 square plus minus 3 square, that is nothing but equal to square root of 16 plus 9, that is square root of 25, it is equal to 5. Right, now we got the magnitude also. Right, the r12 vector also calculated, r12 magnitude also calculated. Now we can substitute in the formula. This f1 vector equal to 9 into 10 to the power 9 q1 q2 divided by r12 cube into r12 vector. Now we can substitute the value. 9 into 10 to the power 9, q1 is 50 into 10 to the power minus 6, q2 is 10 into 10 to the power minus 6 divided by this magnitude is 5 cube. Right, the vector is minus 4i minus 3k, j is not available, j is 0. Right, by simplifying this, what we got, 0.036, simplification of this term is 0.036. Then this vector minus 4i vector minus 3k vector, you can multiply inside, so that what we got, minus 0.144 I vector minus 0.108 k vector. Right, now we got the vector in the force F2 in a vector form, right, because the 2 points are given, so we can use the. Right, we'll go to the second problem. The second problem is, there is a triangle is available. At each corner of the triangle, the charges are placed. This is the first corner, second corner and third corner. In each corner, the charges are placed are equal value, 0.25 microcoulomb. Here also 0.25 microcoulomb. The distance also 0.1. It means it is a equilateral triangle. So that angle will be 60 degree. Right, at 3 corners of equilateral triangle, 3 charges are placed. The charges value are equal. The distance also equal. Due to equilateral triangle, it is 60 degree. What is the question? Determine the force on any one of the charge of the configuration shown in diagram. We need to consider one charge. For that, we need to find the force on that charge due to second and third charge. Okay. We will consider this first charge. We will see what is the force on the first charge due to second charge and third charge. Right, we will consider the first charge due to the second charge. What is the force on first charge? Due to the third charge, what is the force on first charge? Right, first we will see first and second charge. So there is a force exists between first and second charge, that is nothing but F12. F12 is the force on the first charge due to second charge. Both are available in the same line. The angle between these two is 0. So we have only one component, that is called horizontal component. Right. Next we will see the force between 1 and 3, that is F13. F13 is the force on the first charge due to third charge, F13. But first charge and third charge is placed at an angle of 60 degree. So what will happen? This F13 will be resolved into two components, horizontal component and vertical component. Right. How will you find this horizontal component? That is nothing but total component multiplied by cos of theta is horizontal component, F13 cos 60. What about vertical component? Total component multiplied by cos of theta is the vertical component. We can easily remember F13 sin 60. Right. So horizontal component is total component multiplied by cos of theta. Vertical component is total component multiplied by sin of theta. Now we have three different components available: F12, F13 sin 60, F13 cos 60. Right? These two are horizontal components. From the diagram itself, we can easily understand that F12, F13 cos theta are horizontal. This is the only vertical component, F13 cos 60. Right? Now we'll find this value one by one. The important thing is here the charges are equal, Q1 equal to Q2 equal to Q3, that is equal to Q. So that the forces also equal, F12 equal to F13, that is equal to F. Because charges are equal and the distance also equal. So the force between the charges will be equal. Q1 Q2 divided by 4 pi epsilon r square. Right? Here we are using the scalar form. Previous problem we used the vector form. Here the scalar form. Q1 is 0.25 into 10 to the power minus 6. Q2 also same, 0.25 10 to the power minus 6. Right? 4 pi epsilon naught value is 8.854 into 10 to the power minus 12. Right? The medium is not given, mean epsilon r will be 1. We will take it as a air medium. Right? Then the distance is 0.1. Right? 0.1 square. So what we got? 0.056 Newton. Right? Whether it is horizontal or vertical component, due to equal charge and equal distance, the force between is 0.06 Newton. Right? Now we'll find the components one by one. So F12 is the force experienced by Q1 because of Q2. F13 is the force experienced by Q1 because of Q3. That already we discussed. Right. Now we'll see the horizontal component. There are two horizontal components, F12 plus F13 cos theta. Right? F12 and F3 both are equal. We can substitute 0.056 plus 0.056 into cos 60 will be 1 by 2. So it will be 0.084 Newton, horizontal component. What is vertical component? F13 sin theta. 0.056 into sin 60 is root 3 by 2. So it is 0.04849 Newton. Right? So now we got the horizontal component and vertical component. Then we can find the total force. That is nothing but square root of Fh square plus Fe square. Right? By substituting the value, we got 0.097 Newton. Right? So finally what we got? 0.097 Newton. Right? I will explain again. So this F12 is the force on first charge due to the second. Only horizontal. There is no vertical because both are available in the same line. F13 is the force on first charge due to third, but it is available at an angle of 60 degrees. So it is resolved into horizontal component and vertical component. So that we are treated these two are horizontal. This is the vertical. We calculated this force one by one. This force value will be equal, that already calculated, 0.056. From this we can calculate the total force, 0.097 Newton. The distance and force between the charges. We can easily calculate what is the distance between the charges and what is the force between the charges. Then electric field can be calculated. That is the important thing. Electric field can be calculated from the Coulombs law. But what are the limitations available? The law is applicable only for point charges at rest. It is applicable only for the point charges. Then inverse square law is applicable. We are using 1 divided by R12 square. Right? Similarly, charges are arbitrary shape. Right? That is normally it is a sphere. From that what we can understand what is the important point. Coulombs law is an implication of Gauss law. From Gauss law we are deriving the Coulombs law. The direction of force is always from positive charge to negative charge. This is a very common point, you already know. Always the force will start from positive charge and towards the negative charge. Coulombs law employed in electrostatic, only in the static field. Coulomb is the unit of charge. Because of Coulombs law, we are referring the charge unit of the charge as Coulomb. Right? So in this video, we discussed about the Coulombs law, what are the characteristics and how to get the derivation expression for force, and we solved two problems. One is based on scalar, one is based on vector. Then we discussed the application, limitation and important points. Thank you for your cooperation. Welcome viewers. In this video we'll see the displacement density followed by the Gauss law. First we'll see the displacement density. This displacement density denoted by d. So that is nothing but q divided by 4 pi r square. What is that? This is a displacement per unit area. The definition of displacement density is displacement per unit area, q divided by 4 pi r square. Right? It is a vector quantity. So that is given. It is a vector quantity q divided by 4 pi r square. Now we'll see the relation between E and D, electric field intensity and displacement density. You know that electric field intensity is q divided by 4 pi epsilon r square. The general formula for electric field intensity, q divided by 4 pi epsilon r square. I will rewrite this E equal to q divided by 4 pi r square into 1 by epsilon. The epsilon is written separately and q divided by 4 pi r square is written separately. So we know that q divided by 4 pi r square, this is nothing but displacement density. So we can replace this by d. So that is nothing but E equal to d divided by epsilon. Right? D divided by epsilon. You cross multiply this so that epsilon E equal to d, that can be written as d equal to epsilon E. The relation between d and E is given as d equal to epsilon into E. Now we'll see the Gauss law. The Gauss law is flux coming out of a charged body is equal to amount of charge enclosed. Pi equal to q. That is a statement given by the Gauss law. If any charged body is there, the flux will coming out. That flux is equal to the what is the amount of charge enclosed in the body. So that is a statement given. Pi equal to q. Very simple. Charged body is there, from that flux is produced. So that flux is equal to amount of charge enclosed. Right? Both are equal. Pi equal to q. Now we'll go to the proof of this Gauss law. Let us consider one charge is placed at the origin q. We have one small segment, small area, small differential area ds at a distance r meter. The d is the displacement density along with this small segment. Right? See the angle between these two are normal. Both are in same line. The angle between these two is 0. The small segment ds and displacement density both are at an angle of 0 degree. Right? So we have charge q is placed at the origin. One small segment area is available at a distance r meter. Along with that we have displacement density vector. Now we'll see this. What is displacement density? D. D equal to d pi by ds. Flux per unit area. So this d pi is small flux, so that the small area ds. D pi by ds. We are consider the small area, so the flux coming out of the small area also d pi. Right. So we cross multiply this so that d pi equal to d dot ds. So this d dot ds, that is nothing but a vector dot b vector. What is a vector dot b vector? That is ab cos theta. A vector dot b vector equal to ab cos theta. So we can write d dot ds into cos theta. What is the angle between d and ds? In the diagram it is clear. The angle between d and ds is 0 degree. Both are available in the same direction, 0 degree. So cos 0 will be 1. So we can write d pi equal to d dot ds, d into ds. Right. So this d pi flux is the small flux due to the small area. So by integrating on both the side, we'll get the total flux. So integral d pi equal to integral d dot ds. Integral d pi is nothing but pi. That is equal to integral d dot ds. Right. So pi equal to integral d dot ds. We can replace this displacement density as q divided by 4 pi r square, because displacement density vector is q divided by 4 pi r square. So this is constant, so we can take it as outside. Only we have integral ds. What is integral ds? Integral ds is s. S is nothing but surface area. Right. What is the area? Surface area. If any charge, we assume that it is spherical. So it is pi r square. For simplification purpose, we consider 4 pi r square. So this 4 pi r square got cancelled. Finally, what we got? Pi equal to q. The flux coming out of a charged body is equal to amount of charge enclosed. So after simplification, we got that the flux is equal to charge. Now we'll see the applications of Gauss law. What is the main application of Gauss law? Gauss law can be used to solve complex electrostatic problem involving unique symmetrics such as, right? Complex problem can be solved, that is the electric field intensity due to uniformly charged infinite state wire. Uniformly charged, any object uniformly charged, in that we can find the what is the electric field intensity, either due to infinite state wire or infinite plate sheet or spherical cell, right? We can able to find the variation of the electric field intensity of various objects such as infinite state wire, infinite plate sheet and spherical cell. So the main application of Gauss law is finding the variation of electric field inside as well as outside of the object, either straight wire or plate or shell. So based on that, we'll see two problems. One is based on the spherical cell, another one spherical cell with the entire volume. So the application is to find the electric field intensity. So in this problem 1, determine the variation of electric field intensity from point to point for a single spherical cell of charge with radius r1. Right? We are going to find the what is the variation of the electric field intensity for a spherical cell with the charge is available with the radius is r1. We need to find what is the electric field intensity inside as well as outside of this spherical cell. The radius is r1. Right? We'll see the diagram. So we consider that spherical cell has charge only on its surface, not inside. Inside the charges are not available, only on the surface the charges are available. Right, we'll see this diagram. So this is a spherical cell with radius r1. Our aim is to find the variation between E and R. So this R is nothing but imaginary spherical, imaginary sphere, Gaussian spherical surface. We consider Gaussian spherical surface with radius R. So this, when the R increases, small r increases, what will happen to the electric field intensity? That we are going to analyze. Right? R1 is the radius of the spherical cell. The small r is the imaginary spherical surface. Outside we consider that radius is small r. So if the small r, the radius increases, what will happen to the electric field intensity? That we are going to analyze. Right? So this is the first condition, where first we consider r is less than r1. R is less than r1. That is, imaginary radius is less than r1. That is, what is the meaning? The imaginary surface available inside the spherical cell. Right? If r is less than r1 means, if r is less than r1, this r is less than r1 means the imaginary, the Gaussian cylindrical surface, spherical surface available inside. Right? This r is available inside. Right? So we know that E equal to Q divided by 4 pi epsilon r square. But inside the spherical cell, the charges are not available. Only on the surface, the charges are available. So the inside the spherical cell, the charge is 0, Q is 0, so that E is also 0. Right? The case 1, what we consider, R is less than R1, that is, the Gaussian spherical surface available inside the sphere. The formula is Q divided by 4 pi epsilon r square. In this, inside the spherical, that the charges are not available. Only on the surface the charges are available. So the charge is 0. So the electric field intensity also 0 inside the spherical cell. So that is written here. So this is inside of the spherical cell. The charge is, the electric field intensity is not available, 0. Right? This is the first case. R is less than R1. Right. Now we'll go to the second condition. R greater than R1. What is the meaning? This R greater than R1 means this R is available outside the spherical cell. R is greater than R1. What is available in the diagram as it is? This R is located outside. So what will happen? We'll see that if it is located outside, E equal to Q divided by 4 pi epsilon R square. Now the charge is available. Outside the charge is available. In the previous case, inside the charge is not available. Now the charge is available. Now see the relation between E and R. E is directly proportional to 1 by R square. Right? Inversely proportional is there. When R increases, E will decrease. Right? When the radius increases, the E will decrease. Right? So that is clearly given in the diagram. So this is the surface. On the surface, the electric field intensity is maximum. Thereafter, when the radius increases, it is keep on decreases. The electric field intensity will keep on decreases. Because on the surface, the charges are available. So on the surface, the electric field intensity is maximum. Thereafter, when the radius increases, electricity field will be decreases. Similarly, this side also. So from this diagram it is clear, inside there is electric field intensity is 0, on the surface it is maximum. Thereafter when distance increases, electricity field will be decreases on both the sides. So we can easily identify what is the variation of electric field intensity, what is available inside, on the surface and out of the surface. Inside the surface 0, on the surface maximum, thereafter decreases on both the sides. Now we'll go to the second problem. In this, the volume in spherical coordinate is described. Volume, that means the entire volume where the charges are available inside as well as on the surface. In previous problem, the charges are available only on the surface, but here we consider volume. Right? Contains the rho coulomb per meter cube. So entire volume, the charge is available. This is the charge density, rho coulomb per meter cube. So by using Gauss law, we need to determine what is the variation of electric field intensity in the spherical charged body. Right? So the previous problem, charges available only on the surface, but in this, the charges available in the entire volume, inside as well as on the surface. Now we'll see the diagram. Here the radius is A. Previously it is R1, capital R1, now it is A. Radius of the spherical cell is A. This is the imaginary radius. We consider one Gaussian spherical surface with the radius small r. Our aim is to find the variation between this electric field intensity and radius r. When the radius r, imaginary radius increases, what will happen to the electric field intensity? Right? So before that we'll see what is rho. Volume charge density is nothing but Q divided by V. Cross multiply this, Q equal to rho into V. Charge equal to volume charge density multiplied by volume. Right? So Q can be represented as rho into V based on this formula. Now we'll have two different cases. This R is less than A. R is less than A means the imaginary Gaussian spherical surface available inside. Right? So we'll see this. R is less than A. R is less than A means this R is available in the inside of the spherical cell. Now we'll apply the Gauss law. E equal to Q divided by 4 pi epsilon R square. Now Q can be replaced as rho V. We already discussed rho V. So rho divided by 4 pi epsilon R square. What is V? V, volume of the sphere, is nothing but 4 by 3 pi R cube. 4 by 3 pi R cube. What is the value of R here? R is nothing but less than A. Suppose the A is 10 centimeter mean R will be less than 10 centimeter. It may be 9 centimeter or 8 centimeter or 1 centimeter, right? So R value is a known value here because R is less than A. A value is the defined value. A is the radius of the spherical cell. The radius may be 10 centimeter or 20 centimeter. If it is 10 or 20 centimeter, mean R is less than 10 or 20 centimeter. So the value of R is known value. From A, we can easily identify the value of R. So 4 by 3 pi r cube. Now this 4 pi got cancelled. Here R square is there, here R cube is there. So R square got cancelled. So finally what we have, E equal to rho R divided by 3 epsilon. Right? Rho into R divided by 3 into epsilon. Now see the relation between E and R. E is directly proportional to R. When radius increases, E also will increase. E will also increase. What is this here? R? R is the imaginary radius that is now available inside. So when R increases, E also increases. Now we'll see the diagram. See this. When the R increases, electricity field also increases. At the center it is 0. Thereafter, when the R increases, the electricity field increases and reaches the maximum value at the surface, on the surface. Similarly, this side also. So in the previous problem, inside the electric field intensity is 0. But here electric field intensity increases linearly in the inside of the spherical cell because the charge is available in the entire volume of the sphere as a volume charge density, so that the electric field intensity increases, reaches maximum value at this surface. Now we'll go to the second condition, R greater than A. What is R greater than A mean? Similar to this diagram, R is available outside. What the diagram drawn is applicable for second case. R is greater than A. The spherical cell is available, imaginary spherical cell available outside the sphere. Right. Now we'll see the relation. E equal to Q divided by 4 pi epsilon R square. This Q is replaced by rho V. Right. So that can be written as rho divided by 4 pi epsilon R square into V. What is the V here? 4 by 3 pi A cube, not R cube. Previously we have R cube. Why we are using A? Because R is greater than A. Suppose A equal to 10 centimeter means R will be greater than 10 centimeter. It may be 11 centimeter or 100 centimeter or 1000 centimeter. It will go up to infinite. So we cannot use this value R. Only the defined value A can be used here. Because A is the known value, R is it will go up to infinite. Greater than A means it will go up to infinite. But in this case, R less than A means if A is 10 centimeter, R will be automatically less than 10 centimeter. It may be 1 centimeter or 2 centimeter up to 9 centimeter. It's a known value. From A, we can easily identify the value of R. But here greater than R, so R is greater means we cannot that. It will go up to infinite. So we can use only the known value A. A is the known value. So that we are using 4 by 3 pi A cube. Here we are using 4 by 3 pi R cube. Because here A is the known value, but here R is the known value from A, but here R is maybe go up to infinite, so we are using A. Right. So due to that, what will happen? Only this 4 pi got cancelled. So pi A cube divided by 3 epsilon R square. What we got? This R square got not got cancelled. Rho A cube divided by 3 epsilon R square. See the relation between E and R. E is directly proportional to 1 divided by R square. Right? Inversely proportional to R square. When the radius increases, E will decreases in a square manner. E is directly proportional to 1 by R square. See this, that will be reflected in the diagram. So here it is maximum. So when the R increases, the electric field intensity will decreases, not a linear manner, in a parabolic manner, because E is directly proportional to 1 by R square. It keep on decreases on both the side. Right. So in this problem, when the spherical cell, the imaginary spherical cell is inside, if you consider, the electric field intensity increases in a linear manner because charges are available inside. Reaches maximum on the surface, thereafter decreases because E is directly proportional to 1 by r square here, right? So we can easily identify the variation of the electric field intensity in the spherical cell with volume charge density. Inside increases linearly, outside decreases in a parabolic manner. Welcome viewers, in this video we'll see the Biot-Savarts law, definition and derivation. The Biot-Savarts law mainly give the expression for magnetic field intensity. The expression for magnetic field intensity is given by the Biot-Savarts law. We'll see the definition. Steady current flowing through a straight conductor produces magnetic field in the form of concentric circles. When a current is flowing through a straight conductor, what will happen? The magnetic field is produced in the form of concentric circles. The intensity of this magnetic field is given by the Biot-Savarts law. The intensity of this magnetic field is given by this Biot-Savarts law. We'll see the diagram. So this is a straight conductor. The straight conductor is available. The current is flowing through this straight conductor. At point P, we are going to find what is the magnetic field intensity due to this straight conductor, straight current carrying conductor at point P, which is at a distance r meter. AR cap is the unit vector. This is the angle theta. This straight conductor is assumed to be having so many current elements. Current element is nothing but ideal vector. I into dl vector is a current element vector. There are so many current elements available. We consider one current element at this point. Further we can go for integration, right? So this is the straight current carrying conductor. Due to the current, the magnetic field is produced. We are going to find the magnetic field intensity at this point P due to this current carrying conductor, which is located at a distance r vector. AR vector is a unit vector along this. This is the angle theta. The straight current carrying conductor is assumed to be having so many current elements. Consider one current element ideal at this point. This unit vector can be expressed in two different ways. In terms of magnetic field intensity, the H is nothing but magnetic field intensity. DH means magnetic field intensity due to only small current element, only one current element. So the unit vector in terms of magnetic field intensity is given as DH vector divided by DH, vector by scalar, DH vector by DH. In terms of distance vector, it is R vector by R, vector by scalar, R vector by R. So the unit vector can be expressed in terms of magnetic field intensity or in terms of the distance vector. Now we'll see the definition. A straight conductor is assumed to be formed by several segments. Such a segment is called current element. There are so many segments available. That segment is nothing but current element. We consider the current element is nothing but ideal vector. The definition for current element is the ideal vector. Let the magnetic field intensity at point P due to the current element is dH. The H is the magnetic field intensity. dH means only due to one current element. So at point P, magnetic field intensity due to the current element is dH vector. By integrating, we'll get the total magnetic field intensity. Now we'll see the definition. According to Biot-Savarts law, what is the definition given? According to Biot-Savarts law, the magnetic of dH vector is proportional to ideal. Biot-Savarts law, the first statement given, this magnetic field intensity is directly proportional to current element, ideal, and inversely proportional to square of the distance between the element, that is R. Inversely proportional to square of the distance between the current element and field point, right? So it is directly proportional to ideal and inversely proportional to distance between the current element and field point, right? So that is given here. dH is directly proportional to ideal divided by r square, directly proportional to ideal, inversely proportional to r square, and also it is proportional to sine theta, sine of theta. So while equating, we need to introduce one constant, that is 1 divided by 4 pi. So dH equal to 1 divided by 4 pi ideal divided by r square into sine theta. So this is the expression from Biot-Savarts law, but this is the scalar. Scalar, in this it is in the form of scalar. Now we'll see what is the vector form. So in the vector form, we already discussed the unit vector. Unit vector AR is nothing but vector by scalar. From that, DH vector can be written as DH into AR vector, AR cap. Right? So the vector equal to scalar into unit vector. That already we discussed near the diagram. So this DH is nothing but scalar. So we can substitute from the previous equation. Ideal sine theta divided by 4 pi r square into AR vector. So this is in the form of now vector form, magnetic field intensity in vector form. So that can be rewritten as DH vector equal to ideal AR vector, AR cap into sine theta divided by 4 pi r square. Now refer this, A vector cross B vector equal to AB sine theta. A vector dot B vector is AB cos theta. A vector cross product means AB sine theta. Now consider this is ideal is the A vector. AR cap is the B vector. So what will happen? Ideal vector into A vector means ideal AR sine theta. So that is available here. So this ideal AR sine theta can be replaced as ideal vector cross AR vector, AR cap. Like similar this, A vector cross B vector, right? So this is A, this is B, this is sine theta. So AB sine theta is can be written as A vector cross B vector. A vector, that's ideal vector cross AR cap divided by 4 pi r square, right? So based on that, we wrote this expression. But unit vector, one more form is available, r vector by r. In terms of distance vector, it is r vector by r. So replace this AR cap as r vector divided by r, right? So already here one r square is available. So ideal vector cross r vector divided by 4 pi r cube. So this is the magnetic field intensity in the vector form. So by integrating on both the side, we will get the total magnetic field. So integral dH vector equal to integral ideal vector cross r vector divided by 4 pi r cube. So integral dH is h, that is equal to integral ideal vector cross r vector divided by 4 pi r cube. So this is the magnetic field intensity in the scalar form, in the vector form. The previous one, first what we discussed is the scalar form. So from the magnetic field intensity, we can find the magnetic flux density, B also. So there is a relation between B and H, B equal to mu H. So that B equal to mu into, the H is nothing but this value, integral ideal vector cross r vector divided by 4 pi r cube. So now we got the expression for magnetic flux density also, right? So the magnetic field intensity and magnetic flux density expressions are obtained from the Biot-Savarts law. So in this video, we discuss about the Biot-Savarts law, definition, derivation. Finally, we got the expression for magnetic field intensity and magnetic flux density B for the expression. Thank you. Welcome viewers. In this video we'll see the Amperes law definition followed by applications of Amperes law. First we'll say the statement of Amperes law. The statement is the line integral of tangential component of magnetic field intensity H around a closed path is exactly equal to the current enclosed by that path. Suppose if conductor is available, current is flowing through the conductor, the magnetic field is produced in and around the conductor. That magnetic field is equal to amount of current enclosed in the conductor. That is the statement given by the Amperes law. Integral H dot dl equal to I. So when a current is flowing through a conductor, the magnetic field is produced. So the magnetic field is equal to amount of current enclosed in that path. The closed path is required while applying the Amperes law. So in the closed path, the entire magnetic field intensity is equal to current flowing through that closed path, right? So it's a statement given by Ampere law is integral H dot dl equal to I. Now we'll see the applications of Ampere's law. There are three applications available. We'll see one by one. The first application is magnetic field intensity due to long wire. The magnetic field intensity due to finite wire is available in separate video. This is long wire, right? Finite wire means the length is defined, but here the length is not defined. It's a long wire. Now consider the circular loop with radius d meter, right? So refer this diagram. We are considering one circular loop with diameter d. So this is nothing but the conductor. The conductor, current I is flowing through the conductor. So due to this current flow, the magnetic field is produced in and around the conductor. In order to apply the Ampere's law, we construct one circular current loop with radius d meter. According to Ampere's law, what is that? Integral H dot dl equal to I. So the H is constant, so integral dl equal to I. What is integral dl? Integral dl is nothing but perimeter of this circular current loop. For example, this circumference of the circular current loop is nothing but a integral dl. That is integral dl is L. L is nothing but length. Length is nothing but circumference. So that is equal to 2 pi d. Right? So integral H dot dl equal to I. So H into integral dl equal to I. Integral dl is L. L is nothing but perimeter. That is nothing but 2 pi d. Right? So we can replace this integral dl with 2 pi d. So H dot 2 pi d equal to I. So H equal to I divided by 2 pi d. Right? So this is the magnetic field intensity due to a long wire. So this magnetic field intensity depends upon two parameters. What is the current flowing through the conductor and the circular current loop, the radius of the circular current loop d, right? It is inversely proportional. Current is directly proportional, d is inversely proportional, right? So the final expression is H equal to I divided by 2 pi d. Now we'll see the second application. The second application is magnetic field intensity due to the solenoid. Due to long solenoid. This is also a long solenoid. Right? The magnetic field intensity due to normal solenoid available in a separate video. This is application of Ampere's law under that magnetic field intensity due to a long solenoid. You know that the solenoid is an electromagnet. It's an electromagnet. It is formed by winding few turns over a iron rod. Right? One iron rod is there over which if the coils are winded, when the current is flowing through the coil, it becomes electromagnet. So that is nothing but solenoid. Solenoid is a over a iron rod. The windings are available. When the supply is given, it becomes electromagnet. Now consider the solenoid with length L as shown in the diagram. Right? We are going to consider the solenoid with the length L meters. So this is the solenoid. This is iron rod over which the coils are winded. When the supply given, it become electromagnet. The length of the solenoid is L meters. In order to apply Ampere's law, what we need is closed path is needed. When closed path is needed, then only we can apply the Ampere's law. So this closed path is A, B, C, D, A. So this path AB is available inside the solenoid, the CD available outside the solenoid. So that we can analyze what is the magnetic field intensity inside as well as outside of the solenoid. Right? So this is the iron rod over which the coils are available. When the supply given, it become electromagnet. The length of the solenoid is L meter. In order to apply the Ampere's law, we construct one closed loop AB, CD, A is such that AB available inside the solenoid, CD available outside the solenoid. Now we'll see what is the magnetic field intensity inside and outside the solenoid. Let us consider H1 is the magnetic field intensity available inside the solenoid. H1. H2 is the magnetic field intensity outside the solenoid. Right? We assume that we consider H1 is the magnetic field intensity inside the solenoid. H2 is the magnetic field intensity outside the solenoid. Now we can apply the Ampere's law. Apply Ampere's law to the closed path A, B, C, D, A. We'll see what is the Ampere's law. Integral H dot dl equal to I. We need to see what is the work done along this AB, BC, CD and DA. For all four paths, what is the work done? We need to analyze. The work done along AB is H1 into L, because the magnetic field intensity inside the solenoid is H1. So H1 into L, integral H dot dl. So H1 into L. The work done along CD outside is H2L. We assume that magnetic field intensity outside the solenoid is H2, right? So inside the solenoid H1, outside the solenoid H2. The work done along the path AB that is available inside is H1L. Work done along CD that is available outside is H2L. Then what is the work done along BC and DA? So work done along BC and DA is 0. Why? The magnetic field intensity and DL are perpendicular. Both are perpendicular to each other. So the magnetic field intensity in the path BC as well as DA is 0. Only the magnetic field intensity, the work done available along AB and CD. BC and DA is 0 because of perpendicular. So due to that, what we have, H1L plus H2L equal to N into I. The work done inside the solenoid, work done outside the solenoid, that is equal to current. Here N number of turns available, so that it is multiplied by Ni. So H1L plus H2L equal to Ni. Right. Now we'll see what is H1, what is H2. So the entire magnetic flux is flowing through the coil of the solenoid. Right, when the current is passed through the solenoid, the entire current is flowing through the solenoid. That is, the flux outside the solenoid is 0. We assume that entire flux is available only inside the solenoid. Outside the solenoid, the flux is 0. That is, H2 is 0. So that the flux flowing through the least reluctance path. So it will follow the least reluctant path that is available in the iron rod. Outside, the iron rod is not there. So outside, the magnetic field intensity is 0. Why? It follows the least reluctance path. So only H1 is available. H1L equal to Ni. This term become 0. So H1L equal to Ni means from that H1 equal to Ni divided by L. So here also the magnetic field intensity depends upon what is the current flowing through the coil, what is the number of turns in the coil, and what is the length of the solenoid. So these three parameters will decide the magnetic field intensity of long solenoid. H1 equal to Ni divided by L. Now we'll see the third application. The third application is magnetic field intensity due to infinite current sheet. One infinite current sheet is available. In that we are going to find what is the electric field intensity. So before that we see what is current density, right? An infinite current sheet is can be assumed to be formed by several sheets in parallel. Infinite current sheet means there are n number of sheets available that are placed in a parallel, like a notebook. Each and every paper is the parallel is the infinite current sheet. Like that, n number of papers are arranged in a parallel. So linear current density or sheet current density is nothing but current per unit length. Always the density means either area, volume or length will be referred. Here we are referring the length of the current sheet, right? So linear current density is nothing but current per unit length, that is K equal to I divided by delta L, ampere per meter. So I equal to K into delta L. So you can cross multiply this so that I equal to K into delta L. So that can be used in the derivation, right? So we have infinite current sheet is available. We assume that there are n number of sheets available in parallel. So the current density is nothing but current per unit length, ampere per meter. From that we can find current equal to the current density into delta L. I equal to K into delta L. Now we'll see the diagram. So this is nothing but a infinite current sheet. The magnetic field available is H. The infinite current sheet is available. In order to apply Ampere's law, what we need? One closed path. A, B, C, D, A. We construct one closed path A, B, C, D, A in the infinite current sheet. The path is available inside, the path is available outside. The closed path, part is available inside, part available outside. The length of the closed loop is delta L. Right. So an infinite current sheet is shown in diagram. This is the infinite current sheet. Let us consider the rectangular path A, B, C, D, A. A, B, C, D, A. Now we are going to apply the Ampere's law to the closed path A, B, C, D, A. So while applying Ampere's law, definitely we need one closed path. Right. So according to Ampere's law, integral H dot dl equal to I for a closed path A, B, C, D, A. Right. For a closed path A, B, C, D, A. Now that is split into four parts: A, B, B, C, C, D and D, A. So integral H dot dl for a path A, B. Integral H dot dl for a path B, C. Integral H dot dl for a path C, D. Integral H dot dl for a path dA, that is equal to I. So what is the work done along these four different paths? The work done along BC and DA is 0 because the magnetic field intensity is 0 in normal direction. In the previous derivation solenoid also we did like that. For BC and DA it is normal direction, so the magnetic field intensity is 0 for BC as well as DA. What about AB and CD? The magnetic field available in AB and CD. See this, for AB the magnetic field intensity will be H. Similarly for CD the magnetic field intensity will be H. Only for BC and DA it becomes 0 because of normal. Right? So now we can apply this. For a path AB, H into DL. There is no H1, H2. We assumed only H into DL. For BC it is 0 due to normal direction. And CD again H dot DL outside. Then this DA also 0. That is equal to I. I can be replaced as K into DL. That is current density. From the current density we already discussed. Right? So H DL plus H into DL. So it becomes 2H into DL. That is equal to K into DL. The DL got cancelled. 2H equal to K. From that H equal to K divided by 2. So magnetic field intensity due to finite current sheet, the final expression is H equal to K by 2. So this is depends only on the current density of the current sheet. Right? H equal to K divided by 2. So in this video we discuss the Ampere's law statement followed by applications of Amperes law. 3 different applications we discussed: infinite long wire, long solenoid, and infinite current sheet. Thank you.